In a previous section, we learned how to find the graphs of sine and cosine functions and looked at their functional behavior. In this section, we will use this information about the sine and cosine functions to graph the other circular functions. Hello, my name is Tom Atwater, and we will begin by looking at the reciprocal identities of the sine and cosine functions to sketch the graphs of y equals cosecant x and y equals secant x. So here we have the graph of y equals cosecant x, and we're going to use the graph of y equals sine x as the guide function. That is because, of course, cosecant x is the reciprocal of sine. So if we look at sine x, we have it drawn here through its dashed line. And we're going to look specifically at when sine x is 0. Because when sine x is equal to 0, we know that we would have 1 over 0, which is undefined, which is represented by a vertical asymptote for the graph of cosecant x. When the sine curve is positive 1, which would be here and here, we know the reciprocal of 1 is 1, so cosecant is equal to 1. When the sine curve is negative 1, which is here and here, we know the reciprocal of negative 1 is negative 1, so the cosecant is negative 1. When we know that the sine curve is positive, which would be in this section right here, that cosecant has to be positive. And as the sine gets larger and larger, in other words, as it goes in this direction, we would see that the cosecant would have to get smaller and smaller. It's reciprocal. And as the sine curve gets smaller and smaller, we know that cosecant would have to get larger and larger. So therefore, we get a U-shaped curve for the cosecant. It has those vertical asymptotes and those key points of the reciprocal of 1. So that gives us the graph for cosecant. Notice that it will have a period of 2 pi, as does the sine curve, that it does not have an amplitude because amplitude is defined to be half of the distance between the max and min point, and of course there's no max or min for the cosecant curve. So now let's take a look at the secant curve, and we're going to use y equals cosine x as our guide function for the secant of x. So we have y equals cosine x in the dashed red, and we graph from that y equals secant x. All of the same characteristics apply in the sense that we locate where cosine is 0, and that's where we'll have asymptotes. We locate where cosine is 1, and that means the secant is 1, where cosine is negative 1, and that means the secant is negative 1. We get the same U-shaped graph. Let's take a look at each graph in a little more detail and identify basic characteristics, starting with y equals cosecant x. The domain. Well, we'll notice for this, the domain would be all real numbers except for where we have our vertical asymptotes, because of course we cannot plug in those x values. And those turn out to be integer multiples of pi. So it's all real numbers except integer multiples of pi. The range. Well, the range, you can see that cosecant will always be less than negative 1, less than or equal to negative 1, or greater than or equal to positive 1. The graph is, of course, discontinuous, and that's why the domain does not carry the whole set of real numbers. There are no x-intercepts. The period, of course, is 2 pi. There is no amplitude because the amplitude is defined to be half of the distance between the maximum and minimum values, and of course, because they go on to infinity in the positive direction, negative infinity, there is no max or min. In particular, the cosecant curve would display what's called odd symmetry. Next, we'll look at y equals secant x. So this time our guide function is y equals cosine x, and that's drawn in the dashed red. And we're going to look at secant x, which follows the same basic characteristics as cosecant in the sense that it is the reciprocal of cosine. So where cosine is equal to 0, we would have vertical asymptotes for the secant curve. Where the cosine is equal to 1, we would have 1 for the secant curve, and where cosine is equal to -1, we would have -1 for the secant curve. And so you can see that again, the period for secant is also 2 pi. The domain, in this case, is all real numbers except where we have the vertical asymptotes. And let me point out that those specifically are things pi over 2, 3 pi over 2, which means they are odd integer multiples of pi over 2. So the domain is all the real numbers, not including the odd integer multiples of pi over 2. The range, as you can see, would be that set of numbers less than or equal to -1, union greater than or equal to +1. There's no amplitude in this particular case for the same reason as we had before. Like the graphs of the sine and cosine function, the graphs of cosecant and secant functions may be stretched or shrunk both vertically and horizontally. As well, they can be translated vertically or horizontally. And a horizontal translation is called a phase shift. Let's look at an example. Graph the function y equals cosecant of x minus pi over 4 over a 1-period interval. So, as I said, we want to look at the graph of the sine curve first. So let's take a look at that. So here we have our guide function, which I want to point out has already been shifted over. This label here is pi over 4. And this 1.571 is our decimal equivalent to pi over 2. And so on. Here is pi. Here's 3 pi over 2. And here is 2 pi. So you can see it's already, the sine curve has already been shifted to the right by that pi over 4. So all we need to do is take this graph and draw our vertical asymptotes, and then we can draw our U-shapes based on the guide function. So let's take a look at that. Our vertical asymptotes are wherever the sine curve is 0. So we see a vertical asymptote there and here. And again, as a reminder, this is pi over 4 for this vertical asymptote, and this vertical asymptote is 5 pi over 4. And then we see our U-shaped graphs, which are the green graphs, which gives us y equals cosecant of x minus pi over 4.